Hi everyone. We're going to continue where we left off at the last lesson, and we're going to be kind of doing the exact same calculations, but this situation is when we've got a small k value. Okay, and when I'm talking small, I'm referring to the situations we're going to talk about here is when k is less than 1 times 10 to the negative 5. And what that means is these reactions don't really go forward, right? You're not making big amounts, not even remotely big amounts. You're not making anything real. Okay, not real large quantities of product. Okay, so in a situation like this would favor our reactants for sure. Okay, so let's take a look. This is our system. All right, we're decomposing water. That has to happen at a high temperature. And as you can see, the K value for this particular reaction is very, very small. So our system here, the water concentration is 1 mole per liter. Don't get messed up. Don't divide by 2. The vessel's 2. We'll deal with that later. But right now, that's your concentration. So let's set up an ice table, okay? So if I just write out my equilibrium. Okay, so we'll set up our ice table. So my initial concentration of the water was given to us, right? And I have 0 products. So my change, since I'm consuming reactant, it's negative 2x because 2 moles. When I'm making products, I am producing 2x and x. And so my equilibrium concentration is going to be, okay, so that's that. Now, let's write out our Kx equation. So in this situation, products over reactants. Okay, and now let's plug in these concentrations in the equilibrium row. So 2x, all quantities squared, x, 0.1 minus 2x, all quantities squared, and our value for k was 7.2 times 10 to the power negative 18. That was given in the question. All right, so as you can see, it's not a perfect square. We're going to have to find another way to solve for x. All right, so let's just expand these terms. So this is going to be 4x cubed, all right, because 2x, all quantity squared, is 4x squared, times another x is 4x cubed, okay? And then we've got, so we're not going to be able to do what we did before and just take the square root. In this case, we're going to have to employ some other things. But luckily enough, if you notice that this is a super small k, you can make an assumption, and we love assumptions because assumptions make the math easy. Okay? So what you're going to see here is we can use this assumption, all right? So we can use this 100 rule assumption, and you can read all about that 100 rule assumption in your textbook, but I'm going to explain it here. If the concentration to which x is added or subtracted is at least 100, hence the word 100 rule, times greater than x, oh, I'm sorry, than k, then my assumption is valid. Okay, so what that means is, in this situation, remember, this value is so small. Okay, remember what that means. If my k is so small, that means I'm not really going forward. So if I'm not really going forward, I'm not really making any product. having said that, that means I'm not really using any reactant. And remember, it's the reactant that you have a ton of. So if I'm not really using much reactant because it's not going forward, this right here, this change is, I love this word, negligible. Okay? And the reason I like the word negligible, because the minute I see negligible, I think easier math. Thank God. Okay? So if this is negligible because the reaction didn't go forward, we can just do one of these. And now rewrite to this. Now, you're going to have to go back and verify that this thing is valid. If it's not valid, guess what? Math time. Okay? But once we fill this out, and we get 4x cubed, 7.2 times 10 to the power negative 18, multiplied by 0.1 squared. Okay? And when we do that, we take the cube root, divided by 4, cube root. I hope you know where that button is on your calculator. Okay, and then you divide by 4. So you take the cube root first, and then you divide by 4. And then your x, once you get that, now I want you guys to try this on your calculators at home. Do not just take my word for it, because ultimately at some point in your life, you're going to have to do this math. Okay, so once I take the cube root and divide by 4, my x is 2.62 times 10 to the negative 7 moles per liter. Now, here's where we have to actually think about things. Okay? If we look at my assumption here, if the concentration to which x is added is at least 100 times greater, so what I have to do is my concentration of my water initially, all over K, right? And my initial concentration was 0.1 molar over 7.2 times 10 to the negative 18. That's 1.4 times 10 to the power 16. Way bigger. Yes, we can use this. Okay, we can use this assumption. We can make that negligible. This is my value. So then once I have this value of x, my concentration of hydrogen is equal to 2x. So 2 times 2.62 times 10 to the negative 7, which is equal to 5.2 times 10 to the negative 7 moles per liter. And we're going to 2 sig dig, so yes. All right, we love the small k. I oftentimes pretty much say, as long as that thing is smaller than the 1.0 times 10 to the negative 5, that k, it'll work. The assumption will hold. But you know what? When you do this, you have to prove it. So you have to do this 100 rule just to prove it. But pretty much all of the time, if you see a super small one, you're going to be making that value negligible. So I just want to rehash it one more time. It's negligible because your reaction doesn't go forward because the K is so small. So because the K is so small, you're not making product, but more importantly, you're not using reactant. And so since you're not using much reactant, this number, it doesn't change. And if you even wanted to do the math, think about it. I'm just going to actually go to a different color here. Okay, think about it. 0.1 minus 2 times 2.62 times 10 to the negative 7. Okay, think of how little that's going to change. It's still going to be 0.9999, so on and so forth, right? So, 0 there. So do you see how there's hardly any change? It makes your math so much easier if you just get rid of that x. Okay, all right, last question. Let's take a look here. The reaction quotient, all right? So Q is an important thing because the Q is something that we use to talk about actual experiments, okay? So when we sit there and we can calculate an experiment that you're not sure if it's at equilibrium, okay? Because you can't always assume a reaction is at equilibrium. So we're going to apply the same law equation, And then we're going to compare the quotient or the constant to what K is, and then everything's relative to K. So if we want to predict whether a reaction is at equilibrium, Q is going to equal to K. All right. If Q is less than K, Q is going to shift to the right. Okay, and that means you're making products. If Q is greater than K, we are going to shift to the left. All right, so let's take a look at some questions here. My last question, or my last example for the day. All right, so if we take a look here, here is our Q, and you see, or I'm sorry, our K, and you'll see my equation or my exponent not small enough. Okay, we cannot use that assumption. So you're going to hope things are perfect squares. All right, here's our system. And we've got 3 scenarios. We're going to see if the given concentration is in equilibrium. And then we're going to figure out if it's not, we're going to see which way it's going to go, forward or reverse. All right, so for A. So my Q for this system is products over reactants. Okay, so that's what we've got to use. So you don't need to do ice tables or anything because you've got everything here. All right, so for our purposes, let's see. For A, if I look at Q, I'm going to use my NH3. So, oops. Ooh, I got a D there. Hold on. There we go. Okay, I hit a button as usual. So, okay, so when I solve for those numbers, and once again, do the calculations yourself. You have my answer, but you need to make sure that you know how to use your calculator properly. Okay, so when I plug all these into my calculator, I end up with this value. Okay, don't forget you were given a K up here. See, right there. All right, so in this situation, Q is way bigger than K. So since Q is bigger than K, my system is not at equilibrium. We're just going to go up here. And since Q is greater than K, the system's going to shift to the left. Okay. All right. Because you've made too much product, right? Think about it. If my Q is that big, that means it went really forward. Okay. So according to Le Chatelier, I've got to shift to the left to use up that product. All right, for B, let's plug that stuff in. So 2 times 10 to the negative 4 squared all over . Okay, and when I plug all this into my calculatrice, I get, all right, and in this situation, oh, you betcha, Q equals K. So therefore, the system is at equilibrium. I don't know why I write a happy face. Just because it's at equilibrium doesn't mean it's awesome. But you know what? We'll go with it. Lastly, for my situation C, all right, when I plug those values into my calculator, my Q, okay, is this value. So Q in this situation is less than K. So since Q is less than K, that means there's too much reactant. That reaction is not moving forward So it's going to shift right. Right? Just all the way back to Le Chatelier. Because you're not moving forward, we're going to make product. Okay, so that's the way it's going to shift. And now, the fun stuff. All right, I've been talking a lot. There is a boatload of homework. Now, you've got until Friday. So you've got Tuesday and Wednesday for these lessons. Thursday is going to be a catch-up day. This is serious face, you need to try these out, okay? Please contact me if you have any questions or concerns, and I will talk to you soon. Take care, and it's a heat wave. Keep out of the sun unless you got sunscreen on, and stay hydrated.